Hello, linear algebra students. So this is going to be our video over section 1.1. Each video should contain material for that section, so you can look at the homework assignment then. Once we finish that video, take a look at the section 0 video as well, if you didn't do that as well. Remember, you have to complete that chapter 0 or section 0 assignment in order to certify that you've begun the course. Okay, so make sure you do that assignment first before you get started on the content in the course. As always, please let me know if there's any questions or concerns about the course that I can answer for you. Send those over to my email or get in touch with me through D2L or through my math lab, whatever works best for you. Okay, so I'm going to switch over to the document camera view now, and we'll get started. All right, so section 1.1 is about linear equations and linear algebra. Okay, linear equations are something that you have seen. You may not have called them a linear equation, or you perhaps did, but we're going to use them in a different way than you may have used them before to this point. Okay, so a linear equation has a form that's going to be a coefficient times a variable, so a1, x1, add that to another coefficient times a variable, and do that as many times as needed. Okay, and then it ends at some a sub n, x sub n, and then we will set that equal to another coefficient, which we will call b. Okay, and so each one of these coefficients, ai or b, so all the ai's or b's, can be real or complex. And now, in our class, we are going to deal almost exclusively with real values. Not 100% exclusively, but almost exclusively. We will do a little bit with complex numbers various times, but for the most part, we're going to look at real values. And especially here in chapter 1, we're going to be looking at real values. Okay? So notice in this form of a linear equation that each one of these just has a single variable expression. Notice that variable expression is not squared, it's not cubed, it's not divided, it's not multiplied by anything other than that scalar constant. Okay, that scalar constant is the only thing it's multiplied by. So if we look at, say, 3x1 plus 2x2 is equal to 4, well, that's clearly a linear equation, right? Obviously, a linear equation, we have a single variable, so this is a two-variable linear equation. Okay? You know, we can put negative numbers in there without too much worry. Negative 2x1, 5x2, that's going to equal 6. Clearly a linear equation as well. Again, just the single value for x. Negatives aren't a problem. They're still real numbers. Okay. Now we can complicate things a bit. So let's say x2 is equal to 2 times the square root of 6 minus x1 plus x3. Okay. So our linear equation form here, notice, has all the variables to one side and this b on the other side of the equal sign. Okay, but we know that we can do operations, typical add, subtract, multiply, divide type operations. Okay, so I could rearrange these accordingly. Maybe I want to bring the b over to the left-hand side. I'll be left with 0 on the right. Maybe I want to bring a2, x2 over to the right and bring b back, whatever it might be. So the thing is, I just need one copy of each variable. So as I look through here, okay, I just have x2. Okay, that's fine. Okay, now this multiplied, it's a little bit concerning, but I got 2 times the square root of 6. Okay, there's no two variables multiplied by each other there, so not an issue. 2 times x1, well, that's just negative 2x1, so that's okay. And then the plus x3 is separate. So I have 3 variables now, but that's still a linear equation. Okay, so I could do some rewriting here to make it look like that form if I needed to. And when we get to matrix forms and other ways of solving and things like that, that's going to be a skill we may need depending on the problem. Okay, so let's look at that here. So I'm going to distribute this 2 first. So I'm going to have x2 is equal to 2 square root of 6 minus 2x1. Add x3 to it. Okay, and so I want this constant to stay on the right, so I want to move these 2 variables over to the left. So this negative 2x1, when I move it, it's going to come over to the left. So I get 2x1 plus x2. It's already on the left side. Now the x3 I'm going to bring over, so negative x3, and that's going to equal to square root of 6. So now this looks like our form that we have up here as well, okay? So all of that does indicate that is a linear equation, okay? Now we can say if I have 3x1 squared plus 6x2 equals 4, well, I only see x1 and x2 one time, but now my x1 is squared, and that's a problem, okay? So that cannot be a linear equation because I have one of my variables squared, okay? Let's say x3 is equal to 2x2 minus the square root of 6, x1, x2. Okay, well, I don't have any squared variables, but I do have x1 and x2 multiplied by each other, okay? And we cannot have that for a linear equation, okay? So you need one variable in each term with one constant term. Now, it can be that way after you rearrange. It doesn't have to be that way in its original format, but you need that setup in order to have a linear equation, okay? Now, remember, just because a variable is listed multiple times doesn't necessarily mean that you don't have a linear equation. So let's say I have 4x1 minus 5x2 plus 2 is equal to x1. Well, you see the x1 twice, so maybe you get thrown off there, but notice the x1 can just be brought over using algebra. So I would have just 3x1 when I get it to the other side, minus 5x2. And then I can take the 2 to the other side and it'd be negative 2. And now it's in the form that we want, okay? So those are linear equations. Those are what we're going to deal with in linear algebra, okay? Now, specifically, we're going to deal with systems of linear equations, okay? So systems of linear equations, which is we're going to have more than one linear equation that we are dealing with at a time. So systems of linear equations, or sometimes, in fact, I would say many times, we shorten that to just a linear system, okay? A linear system. So write a couple linear equations here. 2x1 minus x2 plus 1.5x3 is equal to 8. And then x1 minus 4x3 is equal to negative 7. And we're going to join those with a brace to indicate that those are a set, those are a system of linear equations. Okay, I have two linear equations, and I want to work them together. We sometimes call them simultaneous linear equations. Okay, now I've already looked at this system before, so I have some information about it already. So for example, if I look at 5, 6.5, 3, okay, I want to see if that's a solution to this system. So I have my ordered triple here, okay, so it looks a lot like coordinates, okay, x, y, z, perhaps you might have seen, you did like a geometry class, but this is x1, x2, x3, so we always read those variables left to right. So if I look at my system, I have 2 times 5 minus 6.5 plus 1.5 times 3, and that's equal to 8. And so 2 times 5 plus minus 6.5 plus 1.5 times 3 is equal to 8. So I've got 10 minus 6.5 plus 4.5 is equal to 8. So 10 minus 6.5 is 3.5. 3.5 plus 4.5 then is 8. So I have 8 is equal to 8. So that checks out. That is a solution of that equation. Now, just because it's a solution of that equation doesn't mean it's a solution of the system. It's got to solve all of the equations in the system. Okay, so let's check that now. So I've got 5x for x1 minus 4 times 3 is equal to negative 7. So I've got 5 minus 12 is equal to negative 7, which is good, right? That's negative 7 is equal to negative 7. I should write that down. Okay, negative 7 equals negative 7. So this does pass as a solution for this system, okay? Now, obviously, we're not going to just be given solutions all the time, okay? Like what I did here, I just said, hey, here's this possible solution. Let's check it, okay? So we're going to have lots of methods for determining those solutions and various properties we can discuss and things we can discuss about systems based on those solutions, okay? So solution is an important thing, so we need a definition for that. So solution is a list of numbers S1 through Sn. That makes all equations in a system true when the values are substituted for the corresponding variables. Okay, so a solution is a list that makes all equations in a system true when the values are substituted for the corresponding variables. Okay, so in this case, so I list here 5, 6.5, 3 is a solution for my system here. Okay. Sorry, let me mess with the focus just a little bit, try to get that just a little clearer for you. Okay. So next thing here, systems. So 2 different systems with the same solution set are called equivalent. Almost fit on my screen there. So systems with the same solution set are equivalent. Okay, or if you prefer, equivalent systems have the same solution set, right? So you could read it kind of in either order there. So if you're 2 systems with the same solution set are called equivalent. Okay. All right, so let's look at a system here. So I've got x1 minus 2x2 is equal to -1. Negative x1 plus 3x2 is equal to 3. Okay. Now, there's plenty of ways you might know to solve systems of equations. It's probably something you did in a high school algebra class. Okay. So substitution and elimination are the most common. You also do graphing frequently. Okay. So this system has x1 and x2. We could have just as easily called those variables x and y, and then we would have a system of equations where we could use our usual graphing techniques, slope-intercept form, things like that, to graph those. I'm going to solve this one just by elimination because it's fairly easy to do here because I have the x1 and negative x1 together. So I'm going to add those. I'm going to take my simultaneous system here and I'm going to add the 2 equations. So x1 minus x1 just gives us 0. Minus 2x2 plus 3x2 is going to give us 1 copy of x2. And then don't forget to add the far right numbers, okay, the constant terms. So -1 plus 3 is going to be 2. So x2 then is 2. And so then I'm going to take that value for x2 and put it back into this system. So I have x1 minus 2 copies of x2, which is 2, equal to -1. So x1 is equal to, oh, got ahead of myself, not equal to yet. So x1 minus 4 is equal to -1. Now I'm going to add 4 to both sides. So x1 is equal to 3. 4 minus 1. So x1 is equal to 3. So my solution then is 3, 2. Even though we found x2 first, remember that your solution should be written with x1 and then x2, or x1 and then x2 and then x3. Right? You want to write those variables in order. Okay. So what that also means is we know that these are 2 different equations of lines. Okay. So one is positive slope, one is a negative slope, right? We could graph these lines. So let's look at that here real quickly. So let's pretend, not pretend, let's just rename x1 to be x and x2 to be y. So I would have x minus 2y is equal to -1, which I would then solve for y if I was going to graph it. So I would have -2y is equal to -1 minus x. So y would be equal to 1/2 plus 1/2 x. And then I could do the same thing with the second equation. So I've got -x plus 3y is equal to 3. So 3y would be equal to 3 plus x, and then divide that by 3, so I would get 1 plus 1/3 x. And I could graph these two lines, right? They both have positive slope. One has a y-intercept at 1/2, one has a y-intercept at 1, so it's not going to be the prettiest graph situation, but since the slopes are different and we know that they intersect at our solution, right, 3, 2. So I can graph one there, the other one there, and then pretend I drew perfect lines, which I did not, but you get the idea of the picture here, right? And these lines extend back this way as well. Okay? So they just have the one point of intersection there. Okay? And that one point of intersection is at 3, 2. Okay? So graphically, if I have two linear systems, two linear equations, I should say, in a linear system. There's three possible results here, right? Either my lines are intersecting, right? And if they're intersecting, they have one solution, right? Just that one dot up there where the two lines intersected, okay? Now, if we go up to higher dimensions, we can change some things. We have some different results, okay? Perhaps the lines are parallel, okay? And if they're parallel, they have no solution, right? That's the definition of parallel lines, is that they don't intersect. So if they don't intersect, then there's not going to be any of those crossing points up there. So we're going to have no solution then. And then we have one more result, which is that they're actually the same line, in which case we have infinite, if I can spell, as I'm making this video, solutions. Okay, so they're actually the same line. Okay. All right, so those are our three sort of possible results, and this will give rise to two main questions that we're going to ask about, which is that does a system of equations have a unique solution? Does it have any solution? Does it have the existence of a solution? And then B, does it have a unique solution? Okay, and I will talk more about those a little later in the video as well. Okay, so let's look at one more relatively easy system to deal with here. So y equals 2x. Y plus 2x equals -7, and 3y minus 6x is equal to 1. Okay? So we're trying to figure out how we can relate these two together. Well, as I look here, we're going to use a part of an elimination method that's going to give rise to some stuff we're going to do with matrices here in a second. So as I look at this, the numbers on the left side here, this is 1y and 2x, but down here it's 3y and 6x. So these are different by a factor of 3. Okay, so if I take this first equation, and I'm going to abuse the notation here a little bit, take this first equation and multiply it by 3. So I get 3y plus 6x is equal to -21. Okay, now make sure you multiply by that constant term on the end. That's a common mistake students make, is they'll say, oh, I need to multiply this by 3, but then they will forget that they also need to multiply the whole thing by 3. That's why I say I'm abusing notation, because I really shouldn't write a single multiplication for both sides of the equal sign like that. But it usually gets the point across. Okay. Now I'm going to take my new equation that I made here. Okay. Since I multiplied both sides, I still have an equation. Okay. If I only multiply one side, then I would have broken that equivalence. Okay. But multiply both sides, I keep that equivalence. So I'm going to add these two. So 3y and 3y is going to give me 6y. So I'm adding just like I did in the previous system. Negative 6x plus 6x is 0. And then 1 minus 21 is a negative 20. Okay. Now I divide both sides by 6. So y is equal to negative 20 divided by 6. Well, those are both even, so that's going to be a negative 10 thirds. So both top and bottom there are even. So we divide both by 2, I'm sorry. I saw the 3 there, it said 3. Divide both by 2. So negative 10 thirds then is y. So I'm going to take that y value and put it back into one of my original equations. So I got negative 10 thirds plus 2x is equal to negative 7. So I just replaced y here. Okay. So I'm going to move the 10 thirds over. So I've got 2x is equal to now 10 thirds, negative 7 plus 10 thirds. So 7 would be 21 thirds. Okay, so I'll show it in some detail here to sort of get our thinking going for the semester. But in general, I won't necessarily show out every one of those steps. And so I've got negative 11 over 3. And now remember, dividing by 2 is the same thing as multiplying by a half. So x then is going to be negative 11 over 6. So my solution set here, or my solution, is going to be negative 11 over 6, negative 10 over 3. Okay. Notice I wrote that xy or x1, x2. Okay, so you want to keep the ordered pair or ordered triple or ordered quadruple as we get more variables. You want to keep those in order. Okay. Now, most often what you deal with in linear algebra is matrices. Okay, so we have this idea of linear equations, and we bring that idea into a matrix. Okay, and then we use matrices as our really driving force for what we talk about in the class, but they're always grounded in the linear equations. Okay, so matrix notation is that we're going to take the essential information of a system the essential information of a linear system is recorded in a square array. Okay, now when we say square array, we're talking about a grid of numbers. Okay, when we say square, we're merely saying that the edges are square, right? It actually could be a rectangle when you look at the whole array together, but we still call that a square array. Or more often, we simply call it a matrix. Okay, so if we look at our systems that we've just talked about, okay, so I'm going to move things around here just a little bit to work with those together. So we have our system that we did first, right? This x1 minus 2x2 is equal to negative 1. Okay, we have that system. And now what I want to do with that system is I want to write the matrix notation for it. Okay. Oh, as we look here, get it all in the frame for you. I have one copy of x1, so I'm going to note that 1. I have negative 2 copies of x2 in that equation, and then I have negative 1 for the constant term. And my next one, I've got negative 1 x1, right? 3 copies of x2, and 3 then for my constant term. So there is my matrix, okay? And notice we form those with brackets, okay? Now let's go down to this other system. All right, so I have y plus 2x equals negative 7, and 3y minus 6x equals 1 that we started with. Okay, so I'm going to take the x terms first because I want these to be in order. So just like I did x1, x2 in the last one, I want to do x then y on this one. So I've got 2 copies of x, 1 copy of y. That's equal to negative 7. And I've got negative 6 copies of x, 3 copies of y, and then 1 for that constant term. So that's my matrix there for that system, okay? Now, as I look at this matrix, so I'm going to pick my system page away here because we're going to work on the matrix now. Get that centered for you. There we go. That looks a lot better. You know, I'll first notice we don't usually write this dashed line, but you will see it occasionally. So that dashed line there is going to represent the equal sign, right? When I wrote down my equation, I went x1, x2 equals. So this dashed line is going to help represent my equal sign. Can kind of help keep you grounded if you need it, but it's typically not seen in the matrix. Okay? When you type answers in my math lab, you will not be typing, you will not be putting that dashed line in there, but sometimes it helps to keep things straight. I know this is x1's column and x2's column, and then my constant column on the other side of the equal sign. So if I can get this where I have x1 equals my answer, I have my solution. Okay? So in this one, for example, I'm going to take these two rows and add them together, just like I did before. Okay? What did we do when we solved that system the first time? We added the two equations. So that's ultimately what I'm doing here in my matrix. I'm taking row 1, and I'm going to add it to row 2, and I'm going to replace row 2. Okay? So my row 1 doesn't change at all. My row 2 now, though, this is 1 plus negative 1 is 0. Negative 2 plus 3 is 1. And negative 1 plus 3 is 2. So now if I put my equal sign back in there, my equals bar, I can see that I have x2 equals 2. Because I have no copies of x1. Okay? Now that we know that, we can plug it in just like we did in the previous system. Just like in the previous way we worked this system, right? It's the same system. So that's useful. Now we can also, though, we can say, well, now that I got rid of x1, I can get rid of x2 up here, and then I'd have both solutions. So as I look here, well, I have 2 copies here. So I'm going to take, I say I have 2 copies. I need 2 copies so that those will add up to 0, right? So I'm going to take 2 copies of the second row, add them to the first row, and replace the first row. Okay, so notice that the row that's getting replaced here each time is the second one I'm writing down. Okay, so let's see what we get. So 2 here, add that to 2 there. 0 here, 2 times 0 is still 0, add that to there, so I get 1. Well, 2 times plus a negative 2 is 0. 2 times 2 is 4, minus 1 gets me 3. And then my second row did not change. So again, I have that x1 is 3 and x2 is 2, just like I wanted. Okay, we got the same result. Okay. And then we can look at the same idea here for the second system. Right, this was my second system that I wrote down. Same idea, I want to take 3 copies of row 1, add them to row 2, and replace row 2. That's ultimately exactly what we did when we worked it by elimination. Okay. So I take those 3 copies here. Okay, that's going to give me 3 times 2 is 6. 6 minus 6 is 0. 3 times 1, I'm sorry, is 3. Add that to 3, I get 6. 3 times negative 7 is negative 21. Add that to 1, I get negative 20. And then my top row is unchanged. Okay, and then what did we do next? We scaled this down, right? We divided both sides by 6. So I'm going to take row 2 and divide it by 6 and use that to replace row 2. And so from there, I got 2, 1, negative 7, 0, 1. And then 20 divided by 6, we said was negative 10 thirds. Okay. And then I want to clear that spot out. So I'm going to do negative row 2, add that to row 1, and replace row 1. Very similar to what we did in the last system. Okay, so I'm going to have 0 and 2 still makes 2. Negative 1 and 1 is going to be 0. 10 thirds plus 7. All right, that's going to give me that same 11 thirds result that I got before. All right, look back at the previous work if you need it. Okay, bottom row is going to stay the same. And then what do I need to do? I need to divide this 2. So I'm going to take row 1 and divide it by 2 and replace row 1. Okay, so I'm going to get 1, 0, negative 11 over 6, 0, 1, negative 10 thirds. So again, my x1 is negative 11 over 6. My x2 is a negative 10 thirds, just like I got in the previous system. Okay? So we can use matrices in this way. Okay, we're going to define some precise terms as far as what operations we're saying we're doing and things like that. So let's write down a couple more systems, make sure we got the hang of some notation here. So next system, I've got x1 minus 2x2 plus x3 is equal to 0. Next one, I have 2x2 minus 8x3 equal to 8. And then I have 5x1 minus 5x3 is equal to 10. Okay, so I want to write a matrix for this. Okay, so first equation, I have x1, x2, x3. So I've got 1x1, negative 2x3, and negative 2x2, I'm sorry, and 1x3. Okay, second row here, notice that x1 is missing. So you've got to make sure you put the 0 here for x1 because there's nothing for it. 2x2 minus 8x3. Then the third equation, now I've got 5x1. Notice I have no x2s, so 9 is 5x3. Okay, now there's 2 different types of matrices we're going to talk about. So notice I haven't written this equal sign column down yet. Okay, so first we're going to talk about the coefficient matrix. Okay, the coefficient matrix just uses the coefficients of the variables. And then more like what we wrote in the previous systems, if I take that same matrix but put the equals side of the equation on here. Oh, I ahead of myself. 0 minus 5 and then 10 here, right, for the third equation. So that's 0. Just fix it that way. Okay, we call this a augmented matrix. Okay, and we will work with both at different times during the semester. We won't always talk about exactly, whether we're using augmented or coefficient, but augmented, you might also see that dashed line representing the equal sign, same idea as the ones we looked at before. Okay, so most often we're looking at augmented, but coefficient matrices have their uses as well. Okay, so we need to talk about the size of a matrix. Okay, the size of a matrix is always rows by columns. We say by for that X term there. Okay, rows by column for a matrix. Okay, so if you look back at the first one, right, this coefficient matrix was 3 by 3. So that's 3 rows, 3 columns along the top. Okay, so if I go down to this augmented matrix, I have 3 rows, 3, but now I have 4 columns along the top. Okay, so the augmented matrix is a 3 by 4. Okay. So as we look at our systems, ultimately what we're doing when we are solving systems is we are finding easier equivalent systems. Okay, we're doing these operations on this to make it easier for us to solve, right? So if I look back at my previous 2 examples here, right? Once I get here, this is easy. I just read off x1 is 3 and x2 is 2. And we know it's equivalent because of the operations we did, okay? And so those operations on a matrix are called row operations. Row operations, okay? And there are 3 types of row operations. The first is replacement. Okay? And replacement is what we did the most of over there when we were solving the systems. That's where I take a coefficient, a scalar value, multiply it by a row, and I'm saying row 1 right now, but just as an example. Add that to another row, say row 2, and then I replace whatever that second row is that's listed there. So R1 and R2 are just examples, right? This could be row 2 and row 1, row 3 and row 2, row 5 and row 6, whatever they are. But the thing that's being replaced is the second one, okay? Our second one is called interchange. Okay, and when you do interchange, you switch 2 rows completely around. Okay, so I have 2 rows, say row 1 and row 2, and I just switch where they are. Okay, I move row 1 up to row 2, and row 2 down to row 1. Okay, and then the third that we did not do any examples of interchange just yet, but the third that we did do some examples of is scaling. That's where I take a value and multiply it by a row or divide it by a row, and I replace that row. So when I divided by 2 or divided by 6 over here in the second system, that was a scaling operation. Okay, and those are our 3-row operations. Okay. Now, most often we are trying to get things to be a triangular matrix. Okay, so a triangular matrix means I've got this matrix here. Okay, and all the numbers over here, these may all be numbers. But then below that down here, I've got a whole bunch of zeros. Okay, so if you look back at our previous matrices, right, this is triangular because I have this diagonal 2 and 1 here, and then everything below it is a 0. Now, for just two equations, that's just one number. Okay, but as we get more and more equations, that may be necessary, right? So this matrix we wrote up here, this augmented matrix, is not quite triangular yet, but we could probably get it to be triangular, okay? Because I only need this 1 0 here, okay? So I'm going to write that matrix down, and we're going to talk just a little bit more about that matrix through this lens. Okay, so I've got my matrix. I'll get it in the camera view for you. That matrix, right, was 1, -2, 1, and 0. And it was 0, 2, -8, and 8. And then the third row, 5, 0, -5, and 10. Okay. I've got my matrix now. We talked about how we want to make this matrix triangular. Okay. And I'll warn you right now that, as you've kind of seen already, this section 1 really has a lot of definitions, a lot of sort of group brunt work that we have to do to sort of get things motivated and started here. So we talked about we want to make this matrix triangular, okay? So I want to get everything below that diagonal. So start in the upper left and just move diagonally. You want to get everything below that to be 0. So I've already got 2 zeros here. So where I need a 0 is where this 5 is, okay? Well, right now that's a 5, and I have a 1 up here, okay? So I want to get this where it will kill off this 5 or cancel off that 5. So I'm going to take -5 copies of row 1 because that will get me a -5. I'm going to add that to row 2 because now -5 times that will be, -5 times 1 will be -5, and -5 plus 5 will be 0. And I'm going to replace row 2. Okay? So let's take a look at what not row 2, I'm sorry, row 3. All right, getting ahead of myself. Row 3. We already have a 0 in row 2. We don't actually want to replace row 2. We want to replace row 3. Okay. All right, so 1, -2, 1, 0. Notice we're not replacing row 1, so it's exactly the same. Row 2 the same way. 0, 2, -8, 8. Not replacing those rows. Okay, row 3 is the row that's being replaced. So -5 times 1 is -5. 5 minus 5 plus 5 is 0. -5 times a -2 is a positive 10. 10 plus 0 is 10. -5 times 1 is a -5. -5 minus 5 is a -10. Okay, you got to be very careful with your signs, S-I-G-N, your positive and negative signs. Make sure you are careful. So we are taking this first row, right? This first row is getting multiplied by -5. Okay, so that's -5 and 5 made 0. -10, positive 10, I'm sorry, and 0 makes positive 10. -5 and -5 makes -10. Now 0 times 5 is 0. And so 0 plus 10 is 10. But you do have to make sure you add that constant column. It gets left off by students more times than you might imagine. Okay, so we've got good news, bad news, right? Good news, now I've got a 0 here like I wanted. Bad news, now I don't have a 0 here like I wanted. Okay, so good news and bad news. Now, as I look at these two rows, I can scale these bottom two rows to make them easier to deal with, okay? Because all of the numbers in row 2 are even, so I can take row 2, divide it by 2, and replace row 2. And all of the rows in all of the numbers in row 3 are multiples of 10, so I can take it and divide it by 10 and replace row 3. So I'm going to do two row operations here kind of at the same time. Because they're scaling operations, they're fairly easy for me to keep track of. I wouldn't recommend doing multiple replacement operations at once because they deal with multiple rows, and you have to make sure you do them in the right order and stick them together. But doing multiple interchange or scaling operations at once is not usually a real problem. Okay, so row 1 is unchanged, so -1, -2, 0, 1, 0. Row 2, then we're going to divide by 2. So 0, 1, -4, and 4. 0, 5, -5, and 5. I don't know why I divided that by 10. I want to divide that by 1, sorry. 1, -1, and 1. All right, we're dividing row 3 by 10, not by 1, not by 2. Okay, so this is promising because now I have these 1s lined up. So I want to get a 0 here, right? Because I'm still trying to get that triangular shape. Okay, so I'm going to take a negative copy of row 2, add it to row 3, and replace row 3 again. So my first row is unchanged. My second row is unchanged. But now I'm going to take a -1 of it and add it to the row below it. So -1 and 1 makes 0. First terms actually 0 and 0 make 0. -1 and 1 make 0. This is going to be a +4 and a +1. Sorry, try that again. A +4 and a -1 is going to make a +3. And now a -4 and a +1 is going to make a -3. Right? Now, as we get the hang of this, you don't have to work out all of these steps every time. We're trying to get the hang of it. So this bottom row now, these are all multiples of 3. So I'm going to take row 3 and divide it by 3 and replace it. So my first row, -1, -2, 0, and 1, 1 and 0. Second row is unchanged. And my third row now is 0, 0, 1, and -1. Okay. So the thing to notice here is, remember, I have this imaginary dashed line that represents my equal sign. So I know now that x3 is equal to -1. So the reason this triangular shape is helpful is I can then take the equation above it and use x3 to find it. So if I go back to this second equation, this is now x2 minus 4x3 is equal to 4. But I know x3 is -1, so I can take x2 minus 4 times a -1 is equal to 4. So x2 plus 4 is equal to 4. So when I subtract that 4 over the other side, I actually get that x2 is 0. Right? And now I can take my first equation. So I'm going to have x1 minus 2x2 plus x3 is equal to 0. But I now know x2 and x3. So this is going to be x1 minus 2 times 0 minus 1 for x3. So x1 is equal to, let me say x1 minus 1 is equal to 0. So x1 is equal to 1. Okay, so that triangular form helps us because once we know one variable, we can then apply that variable up the list and find the remaining variables. Okay, once I know that bottom variable using that triangular form. So once you get to that triangular matrix, you know you have a solution. Okay. Now, we've been using something implicitly here, but we need to write it down as a theorem. So I'm going to write it down back under row operations and triangular matrices that we used before here. And so equivalent matrices, remember an equivalent matrix has the same solution. set. Equivalent matrices are linked by row operations. Okay, equivalent matrices are linked by row operations. So if you can do row operations between two matrices, then you have an equivalent matrix. Okay, and the symbol we use for equivalence is the tilde, the squiggle line. Okay, so when I write that tilde there, I'm saying it's equivalent down here to the next matrix below it. It's equivalent to the next matrix below it. Okay, each one of those are equivalent. Now, what we also know is now that we've found these equations, I could actually write another equivalent matrix. This has x1 is equal to 1, x2 is equal to 0, and x3 is equal to -1. Okay, where I have zeros. And so this matrix is almost triangular both ways. Now, we don't necessarily need that for this particular system, but we have that information built in right here, right? These are actually a system of equations, just like the system of equations we started with. And that system is equivalent to the system that we began with. Okay? So equivalent matrices are linked by row operations. Okay? So a question might ask you to determine if a system is consistent. Okay, so if I take x1 minus 2x2 plus x3 is equal to 0, and x2 minus 4x3 equal to 4, and x3 is equal to 3. Okay, notice a couple of things here. I wrote these where the variables lined up. Okay, I did not do that in the previous one because I wanted to emphasize that you got to make sure you get those zeros in there if they're not lined up. But it's very common to write these with the variables kind of in columns so that it's easier to recognize that. Now, the question is this consistent? Okay, so consistent merely means it has a solution. Now, it may have more than one solution, but to be consistent, it just has to have a solution. Okay, so as I look at that system, it's already triangular. If I wrote out the matrix for that, it would be a triangular matrix, right? I know x3 equals 3, so it goes up to the x3. If I plug that in, I'll find x2. Then once I know x2 and x3, I can plug both of those in and find x1. Okay, so this has to be consistent. It's triangular. Okay, no question, it has to be consistent. Okay, so if you can get your system to be triangular, you will have a consistent system. Okay, that's your challenge. Okay, now another style of question that you'll see, let me go to another brand new page here for this web. Another style of question you'll see is what values will make a system consistent. Okay, so if I take the following system here, I'm going to have 2x1 minus x2 is equal to h, and negative 6x1 plus 3x2 is equal to k. Okay. I'm going to have this system. I want to figure out what h and k make the system consistent. Okay. So I'm going to write the matrix. So I've got 2, -1, h, -6, 3, k. I'm going to go ahead and put the dashed line for the equal sign in there for this. So as I look here now, I've got a 2 and a -6. So if I take 3 copies up here, I'll get a 6 in this position. And I can put that with the -6 below it, and 6 minus 6 will be 0. So if I take 3 of row 1, add it to row 2, and replace row 2. So I'm doing a replacement operation. So I know my matrix will be equivalent. Okay, so row 1 is unchanged. Row 2 now, I'm multiplying by 3. So 3 times 2 is 6. I add that to negative 6. 6 minus 6 is going to be 0. So negative 1 times 3 is negative 3. Negative 3 plus 3 is also 0. Okay, that's an interesting result. And then I've got 3 times h plus k. So I've got 3h plus k. Right, they're variables. You can still keep them, add them together. Nothing too problematic there. Okay, so 3h plus k. Okay, now looking at this equation, right, what we have here is that I have 0 on the left side. On the right side, maybe I have 0, but if I don't have 0, then I'll have 0 equals 7. Well, that's not going to work, right? Or 0 equals a, where a isn't 0, right? That'd be a problem. Okay, I can't have 0 equaling something that isn't 0. Okay, so what I need then is I need this 3h plus k to be 0. If it's not 0, then I don't have a system. I don't have a consistent system. Okay, so I need 3h plus k to be 0. Well, I can't give a specific value for h and k, but I can say that k will have to be equal to negative 3h. Okay, so whatever I pick out for k, that determines h, or whatever I pick out for h will determine k. Okay, so what values of h and k make that consistent? Well, it's when 3h plus k is 0, or when k is equal to negative 3h. Okay, so to be a consistent system, you can't have the leading entry. Okay, so I used a new term there. I told you there's a lot of vocabulary in these early sections. Okay, so the leading entry is the first non-zero entry. Okay, leading entry. First non-zero entry. Okay, so as I look here, 2 is my leading entry in the first row. But the second row, the leading entry is this 3h plus k. Okay, so if the leading entry is in the far right column, if the leading entry, a little bit of a long theorem here, but we'll get it written down. The leading entry of an augmented matrix, so remember this is our augmented matrix, not our coefficient matrix, is in the far right column, then it must equal 0 to be a consistent system. Okay? The leading entry of an augmented matrix is in the far right column, far, not for, far right column, then it must equal 0 to be a consistent system. Okay? If the far right column is the leading entry in a row and it's not 0, then we say that system is inconsistent or that it has no solutions. Okay? So there are 2 main questions that we're going to pursue as we go forward into our next sections. Okay? So to wrap up here, section 1, 2 main questions. First question is, does a solution exist? Second question, is the solution unique? Is there only one solution, or are there many solutions? Okay. So those are our 2 main questions that we're going to continue looking at in future sections. Okay. Now it's important that you don't consider the video to be the only material you have for each section. Remember, you've got access to the e-text through My Math Lab. Right? If you have a physical copy of the textbook, that works as well. And you can always email me, get in touch with me, things like that. Check the syllabus, make sure you are keeping up with due dates and when quizzes need to be completed by, and any information about the test as well. Go back and look at the syllabus video, the section 0 video, or look at the syllabus itself to help you answer a lot of those questions. Okay, so that finishes our section 1 video, or section 1.1 video. We'll continue to section 1.2 in the next video.